Control structure integrated design of thermoelastic metastructures for space applications. And first of all, to give you a bit of background on my university, which is the University of the Bundeswehr in Munich, we are building a satellite which is called Athene 1 that is to be launched 2025 already, and there are 13 scientific experiments on it, for example for radiation protection or structural event monitoring, and one experiment will be about, or we called it modern structure experiment, where we will try to bring metamaterials into space. So this is the outline of my presentation, and let me start with the introduction. So what are thermoelastic metamaterials? Thermoelastic metamaterials are, as the name already says, for designing the thermal expansion behavior. And how does this work? You take a triangular mechanism where you combine two materials that have a different CTE, and now if you heat the structure, the hypotenuses will elongate much more than the legs, and you have a loose in height. So doing this, you can design the thermal expansion behavior. You can imagine if you flip those materials, you can also go for very high coefficients of thermal expansions. And what are the main geometric parameters for designing this kind of mechanisms? This is mainly the angle phi, the edge length A, and if you implement it, also the thickness T. And we made some first investigations. Here you see the CTE and the angle phi and the edge length A. So you see, if you go for very low angles and very high edge length, you can reach very high negative thermal expansion. So if you now take this building block, these mechanisms, you can arrange it to 3D unit cells and build 3D lattices to design arbitrary structures. Or what we did, we designed a unit cell for unidirectional expansion, and we added a cone-shaped activation structure that we can apply heating elements that are space qualified, and we want to print multi-cell actuators, and we already printed a test structure at the Institute of Material Science by my colleague Isabel Prestes. And let me now talk about the challenge, which is high precision instruments on satellites. So if you look at satellites, you have very high thermal loads when the satellite orbits the Earth. It's sometimes in the Earth, sometimes in the sun, and behind the Earth it's in the shadow, so it gets warm and cold. And also they are very highly alternating. In the low Earth orbits, it's all 90 minutes is one orbit, and at the same time you need high thermal stability. Here I put a scheme of a satellite where you see the solar cells, and this orange tubes shall illustrate high precision instruments, and now you want to be highly thermal stable within these instruments. Also the relative position of these instruments, if you want to have different images of the Earth, for example, shall be constant. And also here you have other heat sources, which is depicted here in red, for example batteries or other instruments that need to be heated. And if we now look at high precision instruments more specifically, you have a mechanical structure that defines the relative distance between the sensors and the mirrors, and you can imagine it has to be very constant, this distance, that the performance of the instrument is high. And now if you look at this mechanical structures more specifically, you have this high thermal loads, and those thermal loads are different for each point of the satellite and also for each point of the structure. And these high thermal loads lead to the deformation of this mechanical structure. And normally you would take materials with a very low CTE, for example 0 dur, or you keep the structure at one temperature with a heating system. And here we want to do it with metamaterials and add a control. And this brings me to sum up the introduction. So you have this mechanical structure, and now there are two questions. How can we implement such a structure, and how can we design it? And now I want to talk about the structural design task. So let's look at the thermoelastic problem as a black box. So the input are the radiation loads, and the output are defined distances or rotation, and the design parameters what we have are the materials elements, and where to put the control, where to measure it, and which control to apply. And as we are on a satellite, there are also other restrictions that we have to fulfill. These are the mission loads. For example, you have the static acceleration of the launcher, or you have to have a minimum eigenfrequency, a minimum stiffness, and maximum mass on the satellite. And there are other mission requirements. For example, you have to use these screws or exactly these supports, and so on. And now, talking about the design task. So in fact, it's the synthesis of a metastructure here for building this highly thermostable structure. And you could think of different possibilities. You could think of multi-material topology optimization, or you could think building this whole structure out of a periodic pattern and then functionally graded. Or you can do a kinematic synthesis. You can take these building blocks. I showed you this triangular building blocks and build it on one level upper and build there a mechanism. Or you can define a macroscopic topology, on the one hand a ground structure approach that you know already from truss optimization, or another macroscopic topology. And here we did those two approaches. We defined the topology of a functional element, which I already showed you, which is the multi-cell actuator, and we looked where to position them. And this brings me to the two approaches I want to present you. First of all, you have to find a suitable type of structural design. So we decided to go for a truss, as we have well-defined joints, and also the printer, our multi-material printer, has a limited design space, so we couldn't print the whole structure with one job, so we have to have these elements and we have to join them afterwards. And also, doing this approach, hybrid trusses are possible, so you can think of being most of the elements of aluminium, which is highly structurally efficient and at the same time very cheap, and go for those multi-material elements where it's necessary. And method one is a simple comparison. So you define the structure and you compare the different solutions. So I show you a very simple approach right now. So I take this macroscopic topology, which is this two-cell truss, and my only design variable in this case is where this actuator should sit, this multi-material actuator. And what are the load cases? I put here two load cases. I evaluated the eigenfrequency and the radiation loads while orbiting. And the performance metrics of which individual is the best is the first eigenfrequency, the maximum deformation in open loop, or the maximum deformation in closed loop. And here I put one little intersection. So how do I calculate the deformation under radiation loads? If you look at the sun vector and the satellite orbiting the Earth, you see here in yellow if it's in the sun, and in black if it's an eclipse. And if you now look at the satellites more specifically, I put the truss as an experiment on the outside of the satellite, and I calculate the radiation loads that come to the structure, and I kind of measure those radiation loads and save them in a vector or a matrix. And then for the transient responses, I calculate them using a standard state space linearized system. This is computationally more efficient. Also, I can add a controller and also investigate that. So again, this is the setting of the problem and what are the first results. So if you here look where to put the actuator, if you want to have a maximum stiff structure, it's kind of intuitive that you shouldn't place the actuator on position 2, 9, 5 and 12, but rather on 1, 8 and 15. And if you look where the deformation is minimal, it's a good idea to put the actuator on position 2 and 9. And of course, it's not a good idea to put the actuator on position 8 or the orange positions, as they are perpendicular to the control distance or constrained within the supports. So what you would have now to do is to find a Pareto optimal solution, or if the mission requirement is to have this minimum eigenfrequency, you say I allow every solutions that fulfill this eigenfrequency requirement. And but the thing is, doing this approach, you cannot optimize this macroscopic topology. And now we tried another approach. We use this ground structure approach that you know from truss optimization, and we try to do it with a genetic algorithm. So I put this ground structure on the satellite, which is very rough at the moment, and I have two design variables now, the position of the actuator and the thickness of the elements, and the load case in this case was only a hot case and a cold case, so if it's fully in the sun, fully in the eclipse. And the performance metrics here are the eigenfrequency, the mass, and the maximum deformation. And also the actuators have a minimum and maximum length that you can that you can define before starting the algorithm. So the actuator is not dependent on the ground structure that has shorter elements or longer elements. And yeah, these are my first results. We calculated 25 generation. Here depicted is the best individual of every generation, and you see the mass distribution gets more homogeneous, and the position of the actuator seems to be kind of converging. But these are very first results, so from Friday, I think. So this is, I wanted to show you to be able to discuss with you about this, but I have to work on this. And yeah, this is what I wanted to show you. And let me now come to the conclusion. So I showed you how to bring thermoelastic metamaterials in the application of high precision instruments on satellites, and there were two questions to be answered: how to implement this and how to design this metamaterial or the metastructures. And we want to implement it using a truss because we think this is a suitable type of structural design. And for the design, I presented you an approach, the control structure integrated design of thermoelastic metastructures. And as an outlook, we have to systematically investigate this approach, and we have to design this in orbit validation experiments where we want to put the structure on a satellite and measure the performance. And Yeah, this brings me to an end. First of all, I want to thank my collaborators, which is the Institute of Material Science. They do the additive manufacturing, especially my colleague Isabel Prestes. The Institute of Space Technology, Space Applications, where I can use the control algorithms, and of course my funders, which is the Zentrum für Digitalisierung und Technologieforschung of the Bundeswehr, and of course my mission, which is the Seranis mission, where I'm working about, and last but not least, thank you for your kind attendance.